All right, so we just finished Chapter 5 on systems of equations and inequalities. Chapter 6 is on matrices and determinants and applications. This is linear algebra. Now, obviously, Chapter 6 is not a full course in linear algebra, but in this chapter, you're just getting a brief look at some of the basic concepts of linear algebra. But what I've decided is that I think it would be best for this playlist, this algebra playlist, to go ahead and skip this chapter, because everything in here is linear algebra. I'm going to do a course on linear algebra, and we'll start out by learning all of these concepts in depth, so even more depth than what they'll show here. So in this playlist, I thought instead what I would do is try and give you a general sense of what linear algebra is and the purpose of it. So linear algebra has different applications. There's different fields that have made use of linear algebra in different ways. Now, I'm not a mathematician. I'm not a PhD in math. I don't know the precise history of how all of this developed. But let me tell you what my assumption would be was the primary reason linear algebra was developed. And then from there, as the subject was developed, experts in other fields came in and realized they could use this subject for other applications as well. So we just finished Chapter 5, Systems of Equations and Inequalities. We solved systems of equations, linear equations, systems of nonlinear equations, but let's focus on systems of linear equations. We started off solving linear equations in 2 variables, then we went to 3 variables, and we stopped there. The main purpose of linear algebra is if you want to solve linear equations going past 3 variables, but way past 3 variables, 100 equations, 100 unknowns, 1,000 equations, 1,000 unknowns, even more than that. Okay, but also, obviously, the real world isn't so simple. Maybe you don't have 1,000 equations and 1,000 unknowns. Maybe you have 500 equations and 1,000 unknowns. Maybe you have 500 unknowns and 1,000 equations. How do you deal with that? But again, we're only talking about linear equations. In linear algebra, we're only dealing with linear equations. Okay, but if you're like me, when I was going through school, you might be thinking, well, who cares? Who cares in the sense that in real life, nothing is linear. Well, some things are, but the vast majority of systems of anything you see around you is not only is it nonlinear, it's extremely nonlinear. Think about hurricanes, the weather, machines, everything's very nonlinear. So who cares about solving 1,000 linear equations with 1,000 unknowns? Okay, well, take a look at this. There was a video I found a few years ago on YouTube, and I couldn't find that exact video. Whenever I do the full introduction to linear algebra in the actual linear algebra course, I'll try and find that video. But I can definitely give you the general gist of it here. So what this is going to show here is we're going to go from a grid of lines like shown here, and then I'm going to play this, and it's going to transform into those lines are going to transform into some other configuration. So here we go. Let me play this. Okay, now, first of all, the lines, they start off straight. They're straight up and down, straight left to right. But imagine they don't even have to start off straight. They could start off all twisted together and curled, and you could still do the same type of transformation to another twisted up, curled configuration of lines. Okay, this kind of process here, these lines changing from one configuration to another, this is very nonlinear, right? This is what nature is like, real life is like. This is the kind of processes that take place in nature and in machines and in everything. Just a nonlinear mess. You know, like a hurricane. If you're trying to model a hurricane, that's a nonlinear mess. I'm not a meteorologist. I don't know how you'd have to model that with, like, I guess, pressure changes and, you know, whatever you have to model that with, whatever parameters you need to model that with. But again, it's going to be just a big mess of nonlinearity. Now, this here is in 2D. But you can imagine you could make a same kind of video like this in 3D, but even past 3D, we can't conceptualize past 3D, but what I mean is you could have some sort of equation or model that has 5 or 6 variables in it, and so you'd have to abstractly think about there would be a 5th, 6th dimension as far as like a 6th axial direction for that 6th variable that would be transforming. So you can imagine doing a video like this with 6 dimensions, just everything's just transforming and twisting and together and not linear at all. And so the video that I couldn't find, it shows a transformation like this. And again, it doesn't have to start off nice and linear, but it shows a transformation like this. And what they do is they zoom in really far to a single point, and then they play the video again and just follow that point from start to finish. And what's interesting is, so here's an image from a calculus textbook, and what they're doing is, so they've got, here's a curled line, right? That's obviously not linear at all. But if you zoom in really close, it's a line. That's definitely a line. I mean, technically it's never a line no matter how far you zoom in. But if you do zoom in close enough, you could model this as a line. That would be a very good model. You could assume that's a line for sure. And so at the start of that transformation video, they zoomed in really close to a point, and it could have been any point, and it was like a line like this. And then they played the video and followed this point, and it remained a line the entire time. It would just change orientation. So it went to like here, and then like here, or maybe the center point wouldn't change if they're keeping that center point in the middle. But I forgot exactly how it went. But the main idea was the line remained a line. It just changed orientation and maybe even position. The center position moved, but it was always a line. And so that's interesting, right? What does that tell you? That tells you that you could hypothetically model a transformation like this, not just in 2D, but however many dimensions, this extremely nonlinear transformation with a system of linear equations. Now, you want to break it up into sufficient pieces. The more pieces you break it up into, the more accurate. So it might have to be a large system of linear equations, but still, if you did it with enough pieces, that would be a really accurate model. A model in the sense that you could predict the positions of any of these points. You could model this. You could predict the positions with respect to time. Then you could take a derivative of that, and you would get the velocities of all the points. Then you could take the derivative of that, get the accelerations. You could fully model this. Okay, now, and one of the things you learn in linear algebra is how you can represent any system of linear equations as matrix multiplication. So you've got AX is equal to B. This is just the coefficient matrix, this A. So if you have like AX plus BY plus CZ is equal to D, well, this would be A1, B1, C1, D1. Then A2X plus B2Y plus C2Z is equal to D2. And then you have 3 equations and 3 unknowns. The coefficients are this A matrix. It's like a 3 by 3 matrix. Then X and B are called vectors because they're one-dimensional matrices. They're like 5 by 1 or 1 by 5. And why they're called vectors, you'll learn exactly what they mean by the idea of a vector in linear algebra. But you learn how, so if you have an equation like this with matrices, you learn how to solve that. And the way you solve it is with very basic math operations, right? Because solving linear equations is very basic. We know that. Linear equations are easy to work with. And so, yes, if you've got 1,000 equations and 1,000 unknowns, that would take a lot of time to solve, but it wouldn't take a lot of time because you would have to sit there and think and try and figure out some puzzle. It would take you so long to solve the puzzle. No, it would, even though it's 1,000 equations and 1,000 unknowns, it's linear equations. You're going to be doing basic operations to solve it. Adding here, subtracting there, then going to the next line, adding there, subtracting there, go to the next line. You just have to do it for 1,000 lines. It's all basic. So it would just take a long time in that sense. Okay, but what do we know of that is good at doing very basic tasks quickly and doing a lot of them? It can do a large amount of very basic tasks very quickly. And not just that, another thing that makes it difficult is keeping track of where you're at. So you don't want to mess up. You don't want to put the minus sign at the wrong spot. That's not like solving a puzzle. That's just, you got to keep track of where you're at. It's still basic stuff. So what's good at doing a large amount of basic tasks very fast and keeping track of everything as it goes? A computer. So a computer can solve these linear equations. It's built for that. These enormous linear equations with a huge amount of unknowns and a huge amount of equations. Okay, now if you do a YouTube search or a Google search on what is linear algebra or an introduction to linear algebra, you might get different types of videos. One type of video is that they're going to be talking about these really abstract concepts like vector spaces, and the linear algebra is the manipulation of vectors and vector spaces and the transformations of like something, all that kind of talk. If you look at the Wikipedia page for linear algebra, it says linear algebra is the branch of mathematics concerned with linear equations, linear maps, and their representations in vector spaces and through matrices. And this one's actually not so abstract. I thought the definition on Wikipedia was even more abstract than this. Okay, you also might find some videos where they're showing linear transformations in space, kind of like this video, but instead linear, and they're showing how vectors transform in space. Or you might get some videos where they're just talking about some of the stuff that we would learn in chapter 6. You're just taking determinants of matrices, you're doing matrix multiplication, inverses of matrices, things like that, operations on matrices. Okay, well, first of all, again, a system of linear equations, you could have the same amount of equations and the same number of unknowns, but you could also have a situation where you have more equations than unknowns or more unknowns than equations. And in those cases, so the coefficient matrix, this B here would be so you had AX plus BY plus CZ is equal to D. This would be the D's. This would be a vector of the D values on the other side of the equal sign. This is the X, the unknown variables. This is the coefficient matrix. But if you have more equations than unknowns, then you're going to have a non-square matrix here. Instead of this being 1,000 by 1,000, this will be 500 by 1,000, or vice versa. And so one of the things when you learn linear algebra is, well, first of all, you just learn about matrix operations, matrix multiplication, because it's all set up. Matrices and matrix operations, multiplying them and all that, is set up around the idea of solving these linear equations. Like matrix multiplication is set up to where if you had, again, A1x plus B1y plus C1z plus D1L and, whatever, however many unknowns, however many equations, when you multiply the coefficient matrix by the variable matrix, you're going to get a 1 by whatever matrix that gives those other values on the other side of the equal sign. So one part of linear algebra is just learning all of these defined matrix operations. The inverse of a matrix. The idea is when you find the inverse of A, so if you multiply the inverse of A on both sides, the inverse of A times A gives the identity matrix, which is like the equivalent of 1 when it comes to matrix operations. So you solve for the unknown variables. This is going to be like a bunch of variables, right? 10 variables. You'll have 10 variables and then a corresponding column of the same dimensions that has the values of those variables. But again, it gets more complicated if you have more equations than unknowns and vice versa. And how do you interpret that? But then if you have any kind of matrix, so it could be a square matrix or a non-square matrix, like a coefficient matrix. That's the idea, right? You're going to be looking at, you have the variable matrix with all the unknowns, but then the main idea is the coefficient matrix, right? So just to make this clear, A1x plus B1y plus C1z is equal to D. And you could do that, but you could extend this to 1,000 equations, 1,000 unknowns, and 1,000 coefficients on each equation. So any equation you're solving in linear algebra is going to be linear like this. So, but what the idea is, if you have a matrix that has, a big 500 by 500 matrix or 500 by 750 matrix, whatever, there's ways you'll learn in linear algebra. There's ways of how you could break that matrix down. You could decompose it into different matrices. Once you get good with linear algebra, you can look at a coefficient matrix and understand things about that system. right? When you learn about, you determine the eigenvalues and eigenvectors of a matrix. That tells you things about the physical system underlying whatever those equations were modeled from. It gets really deep, and that you can really get deep into this. But when it comes to the graphical transformations, when they're showing transformations graphically, linear transformations, there's ways of looking at linear algebra from a graphical standpoint that way. So if you take a coefficient matrix and you multiply it by a variable matrix, the idea is the variable matrix is starting off with an untransformed, let's say XYZ coordinate system. But then you multiply the coefficient matrix by it and you get another vector, right? So this is a vector. It's a vector because, why is it a vector? Because it's just like X, Y, Z. So an X coordinate, a Y coordinate, a Z coordinate, that's a vector. So you can look at this graphically like you're starting off with a vector that's somewhere in 3D space or even 8-dimensional space if you think about it abstractly. You multiply by the coefficient matrix, and then all of space transforms into a linear transformation. So like all the lines have to stay straight and parallel and evenly spaced, and the origin can't move. Then the vector goes to another spot, and that spot is the B vector. AX is equal to B. Okay, so what's that all about? It's just another way of conceptualizing what's happening with these linear equations. If you understand that well, you can be really good at linear algebra, and you can see a coefficient matrix and see the resulting output vector matrix or whatever, and make predictions, and you can understand the system, right? So if you're modeling the weather or whatever, or something complex, and you really understand linear algebra, how the transformations work and everything, you can take a coefficient matrix and break it down and understand it really well. Add things to it, manipulate it in a smart way. Okay, but now all of this abstract talk, these vector spaces and all this really abstract talk, you'll see courses and videos where it's like really abstract. It's like you're not even talking about an actual linear equation anymore. In the sense that, this AX plus BY plus C, when we solve those in algebra, we could imagine those are lines. Those are actual lines that we graph. But it's still talking about linear stuff, but it's getting really abstract. What's that all about? What you can imagine is what they're doing there. You have to learn, okay, what does a vector space mean? What does all of these terms mean? Because they don't want a person constrained to think about a linear equation in just one way. Like you're just stuck at just that, the way you learned about a linear equation in algebra, you're just stuck there. If you can think about it abstractly, then you can apply these linear algebra ideas to anything that is quote unquote linear. So they took a look at these equations in algebra, these basic, mx, y is equal to mx plus b equations in algebra, and said, okay, what is it about these equations that exactly makes them linear? What allows us to solve these systems of equations this way? What is the true property that makes it linear? And they talk about that abstractly, so you can be in any kind of field, and if you realize, okay, you've got these properties of something, that it behaves linearly in the sense of how linear defines what linear is. It's like it's the way things add and the way constants are multiplied by them. Then you could use linear algebra on that system. And a good example of this is systems of differential equations. A linear differential equation, you look at a linear differential equation and it's like, that's not a line. You don't look at that. If you just took algebra, basic algebra, and you look at a linear differential equation, it's like, that's a line. There's no actual like algebra line about it. Like y is equal to mx plus b. But it satisfies the definition of what linear algebra defines to be linear. And so because of that, you could get a system of differential equations and use linear algebra to solve that system. But to recognize when you can do that, you have to learn to think about the subject of linear algebra in that abstract sense. Vector spaces, and what's a vector space? What's a vector? What exactly is a vector? What do you mean by a vector, at least in the linear algebra sense? It's similar to a regular vector, like in 3D space, that you learn in physics. But linear algebra takes that to way past three dimensions. Okay, and now again, as I mentioned at the beginning of the video, you can imagine linear algebra was developed, but then when these subjects are developed, these math subjects are developed, other branches of science and art or wherever look at a math and find ways that they can use it. So like image analysis, you can like an image. Well, an image is a matrix. At each pixel, you've got a gray value and a color value. You could represent that as a big matrix. Well, so you could use matrix operations. There's been ways that have been developed using linear algebra concepts to work with images, or even transformations like graphics softwares and video games. I believe in video games you're going to be using a lot of linear algebra because you're manipulating the pixels. So there's a lot of different applications of linear algebra. Another application is like data retrieval systems, data storage, and you can store data in compartments and use linear algebra to retrieve data. So in those cases, there's no systems of equations and unknowns. But those applications, they're taking advantage of this matrix manipulation and structure. So that's an overview of linear algebra.